Okay, this is the 6-6 notes for Precalculus 2. The last two sections that we'll cover this semester are all about a new concept called vectors. Some of you might have done this a little bit prior to this, let's say in high school, but I find that the majority of people have never done anything like this or with this concept, talking about vectors. So this will be a little bit of a learning curve for some of you. Just realize that these two sections are pretty long. The notes are pretty extensive, but the key is that there's no crazy advanced math going on here. It's just understanding concepts, little tiny concepts as we go. Okay, so I'm gonna read a lot around with this because there's a lot of details that you're gonna have to know. So just in the beginning here, it says in math, quantities that involve magnitude and direction are called vectors. Okay, any quantity that has a magnitude and direction are called vectors. Okay, so let's just hash that out with some simple examples. Okay, suppose you have a big trip planned to the shore. You're currently driving or traveling 65 miles per hour due south on the parkway. Okay, so what if I asked you for the magnitude and the direction of this scenario? So the magnitude in this problem would be the speed. So that would be the 65 miles per hour. Okay, but what would be the direction? Well, to go down the parkway, you clearly have to go south, so the direction would be south. So we would say that this is a vector because we're dealing with magnitude and direction. What about this one? Suppose you're moving into a new apartment and you're pulling a heavy bag of luggage up to 20-degree incline with approximately 50 pounds of force. Well, again, the magnitude this time would not be an example of speed, it would be weight. So this would be 50 pounds would be the magnitude. And the direction of this problem isn't about northeast, south, and west, it's about an angle. So in this scenario it would be 20 degrees from horizontal. Okay, it is very different from what you're used to doing, but you'll see that these concepts are pretty it's breaking things down and understanding what is a vector. Well, a vector always has to do with magnitude and direction. It's worth noting, though, sometimes you're going to have quantities that have a magnitude and no direction. So a vector is having both, but let's say you were talking about the temperature of a room. So 68, 70 degrees Fahrenheit, that's a scenario where you have a temperature which is clearly a magnitude of some kind, but there's no direction to temperature. So in that case, we would call that a scalar. So scalars and vectors are two concepts that often go hand in hand. You learn about scalars that are just a magnitude and vectors that are a magnitude and a direction. Okay, so let's get more into into vectors and what they're all about. So it says a line segment in which a direction has been assigned is called a directed line segment. Okay, so if you look over at the picture over here, we have a line segment from P to Q, but you'll see that an arrow was added to the picture in order to designate direction. So we would call it a directed line segment. So every directed line segment has an initial point, which is where you start, and then you go in the direction you're actually traveling, and you end up at a terminal point. Now, this should be very familiar to you because when we did trig and we did rotations, we always started at an initial point and we ended at a terminal point. You're going to see that a lot of the trig and vector concepts are quite similar in the which they work. Just note that we represent this, if we were to write this specifically, we would call this vector PQ. In geometry, that look like a ray If you remember when you drew array, it was a little arrow on one side. So you actually do that the same way in vector world. So you would do PQ. It says the magnitude of a directed line segment is essentially its length. Okay, so normally you would say, hey, what's the length of this segment? But now you're going to be using a different word. You're going to be using the word magnitude, which makes sense because that's what we were just using before. Every vector has a magnitude and a direction, so take note of that. We also use a very specific terminology to represent the length, in this case, or specifically the magnitude. We put two double lines. So you guys are used to, let's say, lines like this, which means absolute value. So you would put double lines around whatever vector it is in order to signify that you're talking about its magnitude. Just remember, though, that magnitude has to be positive because it deals with length. So just be careful with that. These are just tiny little things to note of. Sometimes you'll find that it's really, let's say, arduous to continually write rays and letters, and like it's arduous to keep writing this for everything. So sometimes they just call a vector by one lowercase letter called v, specifically one that's sort of bold in nature. But worth noting that if you're actually like writing this on a piece of paper, writing it out, it's really hard sometimes to designate whether something is bold or not. So like I can sit here and I can like color this in to make it bold, but normally you're not going to take the time to do that. So another way to distinguish something on a regular piece of paper as a vector is to put the little letter with a little tiny line above it. This is just semantics, little details that you want to take note of, but in reality, we usually use one letter, or we use the end points in order to determine what array is actually going to be. So last thing here, it says each of the following pairs of vectors v and w have either the same direction, magnitude, or both. Vectors are considered equal if they have the same direction and magnitude. So describe the relationship between the following pairs of vectors. Okay, so what would we do down here? So if we looked at these vectors right here, would we say that they are in the same direction? Well, I sure hope so. You can't go in any better or similar direction. Would you say they have the same magnitude? So remember, we're talking about length. So if we looked at these and lined them up, they look perfectly the same in terms of magnitude. So what does that mean? Are they equal? Well, yes, they are, because they have the same direction and magnitude. Okay, what about the next one? So if we look at these two here, would we say that these are going in the same direction? Now, this is direction is very specific. It has to be literally the same exact direction, not approximate. So if you look at these two, these are going at a slightly different angle, so they're definitely going in a different direction. But would we say that they have the same magnitude? Do they appear to have the same length? Well, it is a little misleading because they're going in the same direction, but they do indeed have the same length if you took a tape measure out. So would we say they're equal? Of course we would not, because they have to be both the same direction and magnitude. Okay, what about these two over here? So are they going in the same direction? Well, they're actually going in polar opposite directions. Do they have the same magnitude? It sure does look like they do. They look the same length. But again, are they equal? No, because they both have to be the same magnitude and direction. Last one. If you look at the direction of these do appear to be going in the same direction, but clearly they are different magnitudes. Therefore, again, they are not equal in terms of vectors. So I know this is probably overkill, this bottom part, but I wanted to show you every scenario of what these look like, so you know sometimes when you start learning something, it's not always clear exactly, the letter of the law when it comes to some of these concepts, but right in the beginning here, that's pretty much how we get started. All right, some more vector, and there's a lot to get through. So here's another scenario we're getting up to. So it says a vector can sometimes be multiplied by any real number. It says the diagram shows scenarios of 3 of these. So basically over here on the left, this is your original vector, and then the 3 under here are the multiplications we're gonna be applying. So it says if you multiply a vector by a positive real number, then you're going to change the magnitude but not the direction. Okay, so look at this. So we start with v. Let's say that this is, let's just pick a number. Let's say this is 10. Okay, this is a length of 10, a magnitude of 10. So we go over to 2v, which is clearly going to have a magnitude of 20. Remember, magnitude is just length. We're multiplying by 2. But note, the direction stays exactly the same. So again, if you multiply by a positive real number, change the magnitude but not the direction. What about the second example, a half v? Well, clearly the magnitude is now going to be 5, but the direction is going to stay the same. Now this is also important. What about negative 3 halves times v? So the magnitude of this is basically 10 times 3 halves. So if you take half of 10, which is 5, and multiply by 3, you get 15. So the magnitude of this vector is 15. Now, some of you might be inclined to say negative 15, but you guys know that length cannot be negative. So the magnitude of this would be 15. So the negative has nothing to do with the magnitude. The negative has to do with what actually happened differently here, the direction. So if you multiply by a negative real number, you're going to change the magnitude, but you're also going to change the direction to the complete opposite. So to be clear, the sign, S-I-G-N, signage, is going to deal with the direction in these multiplication problems, which are called scalar multiplication. So this gray box explains the whole detail, including making sure that when you multiply k times v, that you multiply by the absolute value of whatever the number is. So again, in this example, you're taking the original 10 and you're multiplying by the absolute value of negative 3 halves, not negative 3 halves itself. So just a note on that. But this is something you can read up on later, but that's essentially what we were talking about up top so that you are clear on how that all works. Okay, another important aspect of vectors is the addition of vectors. This comes up in several concepts in this section, so definitely something to take note of when we're doing this. We specifically call the addition of vectors the resultant vector. Okay, so what does that look like? Basically, if we start with, let's say, some vector u, we go from one point to another, but then we start where we left off from u, and we start on another vector, let's say v, and we go to a resultant point. You'll see that if you take the initial point of the first vector and the terminal point of the last vector, you're going to create your own vector, which is called the resultant vector. Okay, this resultant vector is basically u plus v. So I know that it might be a little bit weird to sort of say that, but essentially, if you take any two vectors and then draw them out, and we'll talk more about drawing them out later, by the way, but when we draw the vectors out from u and then v, the result is always going to be the vector from the initial point to the terminal point of the two vectors that you actually had. And also, interestingly enough, it creates a very nice triangle. And the triangle is also going to come into importance later on when we do some of the problems, specifically creating a right triangle. Another little tiny topic. So oftentimes, vectors are used with our typical rectangular coordinate system. Okay, so we will be drawing vectors very soon that are going to be, let's say, from the origin to a certain point. So we'll be dealing with that. But it says there's two we always start with a very specific vectors called I and j. These are called unit vectors, and they always have a magnitude of 1. So let's say, again, we, if we looked at this coordinate system right here, right? So this is our typical. So let's say we just did, this is 1, 1, 1, negative 1, negative 1. So if we took the vector from the origin in the direction of the positive x-axis to the number 1, this is called a unit vector because it has a length of 1, a magnitude of 1, and we call it specifically I. So we can use I to actually, and by the way, this is not I as in the imaginary number I. This is completely unique to vectors. We use the variable I to represent this specific vector from 0 to 1 on the x-axis. Just like we use the vector j to represent specifically the vector from 0 to 1 on the y-axis on the positive side of that axis. So we can use these vectors, which we're going to do in the next piece here, in order to create other vectors in the coordinate system. Okay, so let's do that. So it says let's use our previous knowledge of scalar multiplication and the addition of vectors to make some sense of this. Okay, so it says, given the unit vector I, what is the length from the origin 0 to the point A? Okay, so right here. So if you look at this right here, we want to know what that length is. But remember, when we know that if we went from 0 to 1, the length would be I. Okay, or in other words, 1I. So if we wanted to go to, let's say, 2, then that would be a distance of 2I, and so forth. So if we want to go to A, then the length would be AI. Okay, just like that. Alright, so it makes sense that if we're going in this direction here, you can see that if we had, this was 1, right? We know that this length is j. So if we wanted to go to 2, then that would be 2j. So if this distance here is going to be b, then this distance has to be b times j. Okay, so hopefully this helped. Sometimes when I just say it as is, it's tough, but hopefully this helped understand. It seems that we're just multiplying whatever number it is times I in order to create, or times j in order to create that. No, we don't want to use numbers though, because remember the concept here is for all values. So any letter A or any letter B, if we multiply by a scalar, how would we find that piece? Okay, so this is b times j. So if we return to this scenario right here, so let me get rid of the noise here. So if we knew that this was AI and this was b times j, then how would we get this? Well, we would simply just add them. So that's what this is going to be. What is the resultant vector of this problem? It's going to be AI plus b times j. Well, it turns out that every single vector that you can create can be represented by AI plus b times j, which is going to be the standard for actually stating stating what a vector is, for example. So we always represent A as the horizontal component. So yes, A is this component. And B is going to be the vertical component. Yep, so this way, B. Makes sense, right? So what that's going to look like in numbers, we'll get to in 1 second. I know it's a little crazy with variables, but I'll show you that in a second. We also call the sum AI plus B times J a linear combination. So why do I tell you that? Because in the homework and in the labs and in exams, if they say find the linear combination of the vectors, you need to know what that means. Because it is a technical term, but it just simply means state it in AI plus B times J form. That is the key in terms of what linear combination means. And obviously, we will get into examples in a second here that will help distinguish this. The last part of this is very important, so I'm going to box it. So if we were to determine the magnitude of AI, the vector v, which is AI plus bj, we are going to get the following for the magnitude. So remember, magnitude is the double vertical lines. It's always going to be equal to the square root of a squared plus b squared. So hopefully you can look at this and understand why that is. Because if I took the right triangle with a equal to 3 and b equal to 4, let's say, and I want to find this, well, how do I find it? I do the Pythagorean theorem. But what would be the Pythagorean theorem? It would be the square root of 3 squared plus 4 squared, which we would get 5. Well, we knew it was a 3, 4, 5 triangle, but that's the formula, and the formula simply comes from the Pythagorean theorem. No fancy math here. It's just the Pythagorean theorem. That's it. So when we want to find the magnitude of any vector, pair of vector, we can quickly determine it by using this formula when we do so. One small thing as well, while vectors are often written in AI plus B times J form, it could also be written in component form, which we use this terminology. So you don't see this very often in anything else you did. It's little like sideways caret brackets. That is called the component form. So these are essentially the same thing, FYI, these two things. But sometimes they're written one way and sometimes they're written the other. Okay, so you've learned a lot of information here, obviously, right? You've learned a lot of information on different things that have to do with vectors, but now it's about doing examples and applying what you learned so that you understand like why you learned it. So it says basically, what are the directions of each of these problems, 1 and 2? We need to sketch the vector first, and then we have to find its magnitude. Okay, that's the key. So as long as you can do this in the beginning here, you kind of get a good summary of what this is all about. So note, I gave this in linear combination, linear combo form, or component. They mean the same thing, but I made sure to write them both so you can see that they are synonymous to one another in terms of what you do. Obviously, component form is more of a shorthand because you don't have to write the i's and the j's and the plus sign. But I will say that in the textbook and in the notes, you'll probably see it more in linear combination form when you're doing so. So just take note of that. So this is the vector negative 3i plus 4j. Okay, so how do we actually draw this vector? Well, we draw the vector, if it's only vector v, it's coming from the origin as the initial point. Okay, so what is the terminal point? The terminal point is essentially the coordinate a comma b. Well, if you look at the picture, this is in, actually let me write this out a little differently here. So this is in AI plus BJ form, or A comma B. So when we draw the actual vector itself, the terminal point is going to be the coordinate AB. So what is the coordinate AB? It would be negative 3, 4. So we would go over to negative 3 and up 4 to right here. So negative 3, 4. And then we would draw the vector in that direction from there. And this would be our vector V for our problem. It's actually quite basic coordinates work. It's not as hard as you would think it would be. So this would be the vector v. So we would look at this and say, okay, so for this vector v, what is going to be the magnitude? So remember, when we want to find the magnitude of something, we symbolize it, the variable that we have, and we put double vertical lines around it. So if we do so, we would use the formula square root of a squared plus b squared. Well, look at what we have. We already have a and b right here, correct? So let's put it in. So we get the square root of negative 3 squared plus 4 squared. And it's going to end up being very similar to the example I did before. 9 plus 16, which is equal to the square root of 25, which is equal to 5. Remember, magnitude can only be positive, and we're also not dealing with a scenario of an equation. It's just a formula, so the magnitude of this vector would be 5. So we know that it's going in the direction to the left. We'll talk more about how to calculate direction a little later in the lesson, but for now, this is how you draw the vector, and that is going to be its magnitude. So, what about our second example here? Well, you should be, hopefully, just by doing the example in number 1, you're already kind of getting this, and it does sometimes take a little while, but clearly this vector w is going to start at the origin, at the initial point, and we're going to go to the coordinate 2, negative 5. So 2, negative 5 would be right here. So we draw to the point 2, negative 5, and we put a direction arrow on it. So 2, negative 5. So this would be our vector w. Pretty straightforward, right? So that's it, just a very simple vector, but we have to find its magnitude. So the magnitude is going to be the square root of 2 squared, our a, plus our negative 5 squared. So if we do that, we're going to get the square root of 4 plus 25, which is going to be equal to root 29, which is going to be our magnitude, or in other words, layman's terms, the length of our vector. Alrighty, so moving on. It says, both the problems above on the previous page had their initial points at the origin. Okay, well, obviously they did, right? The origin. Specifically, these types of vectors are called positional vectors. Yay. Okay, so it says, for ease of use, it is preferable to always work with positional vectors. Therefore, even if a vector isn't centered at the origin initially, we convert it as follows. Okay, so makes sense. So if you're looking at a problem, and let's say, like in both these scenarios, you were given a problem where the position was at the origin, then this is called a positional vector. So is this, the blue one over here. So both are positional, but what if it wasn't? What happens if you gave like a random vector that was somewhere out in space somewhere? Well, we want to make it so that it's at the origin. So that sounds weird, but I'll show you that it's actually not. So how would we do that? Well, let's say we were given the initial point P, which is x1, y1, and the terminal point P2, which is x2, y2. We can change it into a positional vector by simply using the following formula. Okay, so it appears that it's just subtracting the x components and subtracting the y components to make that happen. So, looking at my picture here, note what I want you to do is just add this arrow to the diagram here. I couldn't make an arrow in my program that I used to do this. It says, let v be the vector with the initial point p1 at negative 1, 3. Okay, so let's write that out. So the initial point is negative 1, 3, to the terminal point 2, 7. As shown on the graph. So this is P1 and this is point 2, P2. Okay, so we have a vector that clearly is not anywhere near the origin. But, so essentially when you're looking at this, you're going, in terms of the vector world of things, working with this vector stinks, basically. It's not any fun. So what we do is we convert this vector to the same vector in magnitude and direction, but instead coming from the origin. So essentially, I'm just going to do like a dot here. Essentially what we need is we need to create a vector that looks the same exact length, this little dash, and in exactly the same direction, but it's coming from the origin. So hopefully when you look at the little dash line I did here, you kind of get an idea of what we're going to do. So to do that, though, what do we need to do? We need to use this formula up here. So let's say we are converting the vector v, right? So let's look at our points. So this is going to be x1, y1, and this is going to be x2, y2. All right, so how do we do this? Well, we first do x2, which is 2, minus x1, which is negative 1, and then times I, which is here, plus y2, which is 7, minus y1, which is 3, times the j, which is here. Okay, very straightforward. So if we do the math, we're going to get 3i plus 4j. So when we look at this, we go, hey, look at that. We actually just turned this line into a positional vector, a single vector that we know of. So let's graph it. So we go, all right, well, let's go to the point. Remember, we always start at 0, 0. So we're going back to these problems, right? So we had a vector of this form. And how did we do it? We took the endpoint and draw it to. So let's do that again. So let's do 3 up 4, which brings us to here. We draw a line to it. We make an arrow. 0.34. And this is essentially, it's a little poorly drawn line here, but it's all right. So this is essentially a positional vector equivalent to this vector that is not positional. So you can see that if we measure this out, it'd be the same length, and it's in exactly the same direction. So they are equal, which means instead of having to deal with this vector, we can more easily deal with this one here. Okay, so that's going to be essentially, you will be doing that a lot, by the way, when you're, well, not a lot, but enough where you want to be able to turn these vectors into something equivalent on the graph. So just take note of that. That will be a part of your your learning phase here. Okay, so moving on here, just a note, this is kind of like, this doesn't go together with what's on top of it. It continues on with what we're doing, but I don't want you to confuse sort of the two here. So this sort of just goes on with more operations when it comes to vectors. So previously we talked about the resultant vector. So how did we do it? We started at a point, we said, okay, so here's one vector, here's another vector. The resultant is going to be going from the initial point to the end point. So that was the addition of two vectors, essentially. So if this was v, this was w, this was v plus w. But we didn't talk about what happens when you actually are given coordinates and you have to work with them. So that's what this is all going to be about. So the first things first. So if you look at the first formula here, if you're given, let's say, vectors with their components, a's and b's, if you want to add those vectors, then what you do is you simply add their components, their respective components, with a plus sign between them. If you wanted to subtract the vectors, we logically subtract their components, but we still add the individual pieces. So be careful with that when you go through and do the math in terms of figuring that out. But in terms of actually doing a problem, so in this scenario, let's say we were given these in component form. So if you look at these coordinates here, so these are component form with the little triangular brackets or caret brackets. So just worth noting, what does that mean exactly? So that means the vector v, we know that this is a1 and we know that this is b1. We know that this is a2 and this is b2. Okay, those are basically the equivalent to doing the vector in linear combination form. So let's say we wanted to do that. How would we do that? We essentially look at v plus w and we've said, okay, in order to do that, we need to add the a components, which are 7 and 6, with an I, and we need to add the b components, which is 3 and negative 9. Just be careful with the negatives. That's why I put double parentheses with negatives, because I don't want that to be like a mathematical error. So if we add them, we get 13i plus, it looks like 6j. Okay, negative 6j. So if it's a negative 6j, we can immediately change that to 13i minus 6j. You could have even done that in the beginning. So that means this is the vector as a result of addition. So v plus w would be 13i minus 6j. So what would happen if you map this entire thing out? You would have a vector from 0, 0 to 7, 3 somewhere. You would have a vector from 7, 3 somewhere, and then you would have another vector to 6, negative 9, and then the resulting vector of that addition would be 13i minus 6j. Okay, so what if we decided to do v minus w? So if we talked about that, remember there's still a plus sign in the middle, but now we're subtracting their components. So we're going to do 7 minus 6i, and we're going to do 3 minus a negative 9j. So we're going to get 1j plus, looks like 12, or 1i plus 12j, which is just I plus 12j. So this would be the subtraction of the vectors. Remember, this is just simple formula work we're doing here. So even though it's like foreign content to most of you, we're just doing mathematical work that we have to hone in on and make sure we get right going through it. But again, remember this, still a plus sign, right? Doesn't matter that it's subtraction. The subtraction is in the component pieces. It's not in the result when you put them together. So just take a note of that. So that would be the subtraction of the vectors. Okay, so again, what about the scalar multiplication? So we obviously, again, we talked about addition and subtraction, but what about scalar multiplication when we actually have numbers involved? Well, we're going to return, let's say, to the same example. 7, 3, 6, negative 9. So what if I ask for the vector 8v in this scenario? Well, what would that look like? Well, you got 7, 3 right here is v, right? So that is the same as 7i plus 3j. So what would we do in order to find 8 times v? The vector v, we would do 8 times 7i plus 3 times, or 8 times 3j. 8, there we go. And that's the craziest 3 ever. Anyway, so we would get 56i plus 24j as our new vector. It kind of makes sense. I guess it's kind of hard to draw, but like if you did the vector, let's say you went over 7 and up 3 to like here, then you would want to vector 8 times the length but in the same direction. So if you did 56, 24, it would probably be like a point over here or something like that. So you'd have the initial vector and then you'd have another vector that's 8 times it. That's just sort of a like a quick drawing of that, but that's basically what's happening here. You're extending it, but it's going to be in the same direction. So I just figured I'd show you a picture of it so at least you can have an idea of what that looks like. Okay, so what about negative 5w? Now note, what did you learn about scalar multiples? So like for this one, as return. So when you multiply by something that's a positive, you're going to change the magnitude but not direction. Here, you're multiplying by a negative, which means you're going to go in the opposite direction, but you're still going to have a magnitude change of 5 times over. So, but mathematically, it's just multiplying each piece by, negative 5, basically. So negative 5 times negative 9j. So you're going to get negative 30i plus 45j as our component. And by the way, since these were given in component form, if you want to put them back that way, you can. 56, 24, and negative 30, 45. Okay, so it doesn't matter. Just if they don't ask, usually you give it to them the way they gave it to you. But I'm not going to be too picky with all that stuff. I just want to make sure you know what you're doing in terms of the vectors and how they all come together. There's also a scenario. So we did addition and subtraction. Here we did scalar. But what if you were asked to do both? Okay, what would that look like? So I'm going to give you sort of a recommendation here. So similar to like a PEMDAS situation, order of operations, I would do the individual multiplication first in sorting this out. That's just my suggestion. So for example, if you did, I would find 2v first. 2v would end up being 10, 4. I would do 5w, which is going to end up being 15, negative 20 for your scenario. So therefore, if we were going to do 2v minus 5w, then what do? So remember, we're subtracting their individual components, so 10 minus 15 times I, but we always use an addition sign in the middle, and then we're subtracting again their b components with j. So if we do that, what are we going to get? We're going to get negative 5i, and then we're going to get 24j as the result, which we could again just make as negative 524 if we wanted to, as the component form of this vector. So notice I did the multiplication first here just to make sure that things didn't go horribly wrong within the problem. I also wanted to point out that we could have done this in a different way. So you could have, let's say, if it was easier to understand and you're having trouble with the subtraction stuff, we could change the vector to this. We could say that 2v is again 10, 4, but negative 5w is going to be negative 15 and positive 20. Okay, when we put them together. And then if we do vector addition for this scenario, we would say, all right, add their component forms for each. So 4 and 20, j, and we would get again negative 5i plus 24j. So I wanted to add that in there just because I do find that students struggle sometimes with the negative, the subtracting of the vectors. So if you could always change it to addition and stick to everything division, as long as you remember that the negative has to go across into the vector. Now just note, there are a ton of properties that deal with vectors. Don't look at this list like, oh my god, I gotta know this, or I have to memorize this. That's not what this is about. All it's showing you is that if you remember the commutative and the associative property in basic math, like commutative property is 1 plus 2 equals 2 plus 1. That is basic math property, but those properties work just as easily for commutative and associative. Note the distributive properties down here, which is usually the third one that we use. These are all rules that are similar to basic math that also work here. Some other one, again here, multiply by 1 gets you the same thing, multiply by 0 gets you 0. So there's a lot of different properties involved with vectors. I'm just listing them out so that you know. Just a small thing here is if you do have a vector who has 0 magnitude and no direction, it is called the 0 vector. I don't think you're going to be using much of that in this class, but it's worth noting only because you'll see right here, it's bolded, it's called the 0 vector. It is in the properties, so in case you get confused with that. But we're not going to be really using that in any applications that we do, so I just wanted to point that out. Okay, so returning to a previous concept, we're going to use it in order to do some example problems. It says, recall that the unit vector was the vector with magnitude 1. So if you recall, we had two unit vectors that we used, I and j. So I was always the one, this direction, j, this direction with 1 unit in length. So it's often very common that because people want to utilize or work with unit vectors, similar to how in trig we always use the unit circle, it often is useful to use unit vectors as a substitute. So it's often very useful to know what the unit vector is in the same direction as a typical vector. So we will be calculating this, and this will be almost certainly on every single homework, lab, and exam that you get, being able to do this. And we use that using the following formula. V over, remember this is the magnitude of V. Okay, magnitude of V. So best way to do this really is to get right into it so that you have an example to work with. Okay, it says 7. Find the unit vector in the same direction as the vector 12, negative 5. Then verify that the unit vector you find has a magnitude of 1. So the second part of the problem we'll worry about later. It's not actually part of a typical problem, but we're going to do it just to show you and that you understand what you're actually doing. So Before I do anything, though, I want to draw this as sort of a sketch. So 12, -5 would put us in the lower fourth quadrant. So we're going to go over to 12-ish. I'm just going to do super, like, abbreviated graph here, right? Not super accurate, but... So let's say we have a vector, 12, -5. Okay, this is going to be our best bet here. It's saying find the unit vector in the same direction as 12, -5. So clearly, 12, -5 is not a unit vector. I mean, you don't have to be... You don't have to. You don't have to really understand this to get that, because if we're going all the way out here, 12, -5, there's no way the length of this line is 1. It's going to be way more than that. So, what are we trying to find in this problem? We're trying to find the unit vector, so the actual vector with a length of 1 that is in the same direction. So this is just an estimate, obviously, but we're trying to find that vector right there. The unit vector, so length of 1, that is in the same direction as our bigger vector. That is what we're trying to find, and we find that using this formula. So what does that entail? Well, that entails knowing the vector. So let me get rid of this real quick. So that entails knowing the vector v, well, we know that, and the magnitude of v, well, we don't know that. So we got to find it. So let's find the magnitude of v. So remember that's equal to the square root of a squared plus b squared. So in this problem, our a and b are -5 and 12. So we're going to do -5 squared. So we're going to get 25 plus 144, which is going to give us the square root of 169, which is 13. So for those of you with your triples, this would create a 5, 12, 13 triangle. If we drew it to the axis like that right triangle, we would get that. So this is a magnitude of 13. So what is this formula asking me to do? It's asking me to do v over the magnitude of v. This is our unit vector. Well, what is v? V is 12i plus -5j. What is the magnitude? It's 13. So it is kind of weird, but look that it actually created an equation. Now, the way it is now is not ideal because we're looking for a vector, which means it's got to be 2 components. So we're going to divide both of these by 13, right? Because we're going to separate the piece into 13 divided by both of them, and we're going to get the vector 12/13i minus 5/13j. So this is actually the answer to the problem, which means that this coordinate here, in order to create a length of 1 for this unit vector, that's got to be the coordinate. 12/13 -5/13 drawn from the origin of that figure. Now, this is essentially the problem that you would be doing, right? You would be working on, you already have the vector, so v is easy, right? So the only thing you really have to do in these problems when you want to find the unit vector is find the magnitude and divide the magnitude by the vector, and that's it. You're done. So even though this is not actually part of the problem, typically, I did ask you to verify that this unit vector right here is actually a unit vector and has a magnitude of 1. So don't do this necessarily unless they ask for it, but I want to show you that what we did was actually legitimate. So how do we do that? Well, we want to find the vector. We want to basically find the magnitude of the unit vector. So how do we do that? We return to the same formula here, right? A square root of a squared plus b squared, but now we have a new a and b right here. So we do the square root of 12/13 squared plus -5/13 squared. Okay, so let's do this, even though it's a little crazy. So it's going to be 144 over 169 plus 25 over 169. Common denominators, we add them together. Remember, don't take any square roots yet. We're going to get 169 over 169, which is the square root of 1, which is, ta-da, dun-dun-dun-dun, 1. So the magnitude of this vector is officially 1, All this does is show you this formula indeed works. If we take any vector divided by its magnitude, we are going to end up with the unit vector in the same direction as that vector. So again, we have our initial vector here. Over on the picture over here, we have our initial vector from 5 to negative 12, or from 0, 0 to negative 5, 12. And then if we want to find this little blue unit vector, that is how we actually find it. And your brain is probably full at this point, but we have more to do, unfortunately. Okay, so at the beginning of the lesson, you learned about vectors and how they have magnitude and direction. Well, all of our instruction so far has dealt with magnitude, essentially. We've talked about generally the direction in which it goes, but we don't know exactly how we measure direction. Well, that is what a lot of what the rest of what we're going to do is about, at least the next 2 pages. It's all about finding the direction of an angle. Okay, that's going to be the key. So I'm just going to read this sort of so you have an idea. So it says essentially, right here, essentially, if we consider the positional vector AB to the right, so the positional vector AB to the right, the angle theta measured rotationally from the x-axis, right here, would be considered the direction of the vector. Okay, so it turns out that the direction is very trig related. Makes sense, right? So if we have a vector, so let's say we just ignore, I'm just going to look weird, but let's say we ignored all this, right? And we just said, hey, this is our vector. Whatever the direction is from the axis to the vector, the angle is going to end up being the direction of that particular vector. That's going to be the key. Now, it seems straightforward, but there are some interesting little elements here that can get a little crazy. So the key is we don't want to actually have to like do super calculations if we can find a shortcut for finding that angle. So if you look at this picture right now, if we created our A's and B's like we did before and created this right triangle out of it, that angle theta can be easily found using trig, specifically the tangent of theta. If you look at this picture, the tangent of theta is opposite over adjacent. So it's going to be B over A. And if we want to find the angle specifically, like right away in terms of that, hey, I got rid of the wrong thing, hold on. If we wanted to find the angle specifically, then we would use the tangent inverse of B over A to find it. So this formula right here, tentatively, we're going to edit it in a second, would give us the measure of the direction of this angle right here. So let's do an easy example to start on a tentative basis. Like I said, it's going to be a little bit altered in a second, but let's do a tentative example. So if you recall, again, put arrows on here. So if you recall, we had this problem earlier in the class where we had this random vector in the middle of a plane from negative 1, 3 to 2, 7. And we did the calculations to find the positional vector 3, 4, which is the bottom vector here, which enabled us to use a positional vector which is equivalent to this vector. So for the purposes of what we're going to do, we can forget that this exists for a second. So what do we have? We have the vector at the bottom here, this positional vector, which goes to the point 3, 4. Okay? So let's say I already found the magnitude previously, and that was 5, I believe, of this vector. So let's say they asked you for the direction. Well, the direction, again, is going to be the rotation from the initial side, the x-axis, to the vector. And that, by the way, that's going to be the same for wherever the vector is. It's always going to rotate. It could rotate all the way around. So angles could be anywhere from 0 to 360, not including. So just other than, it won't be usually quadrantal angles, but yeah, we'll get to that in a second. But that is going to be the angle. So how do we find that? Well, we actually don't have to draw the triangle up here. We can just use the formula tangent inverse of B over A. So look at our coordinate 3, 4. Well, that's AB. So we're going to take B, which is 4, and actually let me write it out for you. So B over A, which is going to be the tangent inverse of b, which is 4, over a, which is 3. If you put this into the calculator, you're going to get 53.13 degrees. And everything we're going to do is in degrees for vectors, by the way. Even though I know you're used to radians, and that's a good thing, for the sake of this section, it's going to be all in degrees. So that means this angle is 53.13 degrees and is officially the direction of our vector. So if you're in the beginning of a problem asked to find the magnitude and direction of a vector, this is what you would do. Okay, so as I said before, I said that this was a tentative formula, and I'll explain why. So if you try to use this formula as is outside of the first quadrant, then it often results in unintended consequences, answers that aren't particularly correct or right on the money. So if you notice, the vector here in this is in quadrant 1, so it worked fine. But what I'm going to do is I'm going to, and this is taught differently in different ways by different professors, textbooks, blah, blah, blah. I have my own way of doing it, which is very helpful, and I'm going to go through it in detail. And I like to give problems like this on exams, by the way, and notes, labs and all that stuff. So I'm going to do sort of my own thing when it comes to this. So I'm going to read this. It says, one thing to take note of is that when a vector is not in the first quadrant, we get unintended results. For a reason, we define the following formula as the reference angle of some non-quadrantal vector AB. Okay, the key word here, by the way, is reference angle. Okay, if you look back at our problem here, note, isn't this angle the reference angle as if this was a triangle? Hopefully you remember reference angles are always drawn to the x-axis. Remember, to the x-axis, reference angle, right? X-axis. So the formula that I provide here gives you the reference angle. It doesn't give you the direction necessarily. Sometimes it will, but it gives you primarily the reference angle, and I'm going to show you with formulas how to do the rest. In reality, this can be very simple, or you can make it complicated for yourself. In previous semesters, I took less time to go over this. I've now decided to take more time because I want students to really understand what this is about. So let's just look at the formulas before we get into anything. So according to this formula, again, is going to give you the reference angle. So let's just see what the direction is going to be of the angle. So I want you to look at this picture right here. So you're looking, actually, before that, let's look at the original picture. So it says, if you're in quadrant 1, the direction angle of the vector will be what? Well, if you use this formula, the tangent inverse of b over a, so let's just say, for argument's sake, instead of parentheses, we did absolute value, right? Would that have changed anything? No, because everything was in positive. We still would get 53.13 degrees. So what did we actually end up getting as our reference angle? 53.13 degrees. What did we end up getting as our direction? 53.13 degrees, which means the direction angle of the vector in this case will always be whatever your answer is, theta. Okay, so maybe you understood that, maybe you didn't. Hopefully when we go through each one of these 4 or the remaining 3, you'll catch on a little bit. So let's just say that we went into quadrant 2. So I want you to look at this picture right here. So let's say that this right here is our vector. If we use this formula, it is going to calculate the reference angle. So that means that you're going to end up getting theta right here. Okay, so right now we have a vector with theta to the x-axis in the second quadrant. My question is that the direction of this vector? Well, you might have inklings to that. It'd be great if this was an in-person lesson because there's nobody to answer. Maybe my dog who's sitting over in the corner. But the answer is no, it isn't. The direction is always taken from the x-axis. Hello. Right there. So that's the direction. So how do we find that if we know what theta is? Well, look at the entire line here. It's 180 degrees. So the direction angle of a vector in the second quadrant is going to be 180 minus whatever you get for your reference angle. Okay, hopefully you understand that. So again, this formula is going to get you only the reference angle, which is right here. We need to subtract from 180 to get the orange angle right here, which is the actual direction of the vector, because we need to know what that measure is so we know the direction will tell you what quadrant it's going to be in. That's a very important aspect of this. Let's try this again. So if you look at quadrant 3 in this scenario, let me go to blue here. So if you look at quadrant 3, if you wanted to use this formula, it would give you the reference angle, which is right here, to the x-axis of the vector. So here's the vector right here. The reference angle would be that little theta right there. But what's the direction? The direction is this, all of this. So how do I find that angle? I take theta, which is that little angle, and add what to it? Hopefully some of you are going, oh, we got to add 180 to it in order to get the direction of that. So that's the formula for quadrant 3 direction angles. Last one, quadrant 4. If we use this formula to find theta, we are going to get the reference angle right here, drawn from the vector, which is this, to the x-axis. All review. But what is the actual direction? The direction is this gigantic rotation. So the question is how do we find that gigantic rotation? Well, we know the direction. If we kept on going with that direction to this, we would get 360 degrees. So we have to take the theta out to get the full angle. So the last formula is going to be 360 minus theta. Okay, so this right here is important. Maybe you have to go through it again. I don't know. But the key is that this formula here is, I don't think it's in the textbook, just the way it's written like this, but this is the way I like to do it. Students seem to really understand it this way. Basically, this is not the formula for the direction. It's the formula for the reference angle in which these formulas get you the direction. So these are the direction angles right here. So use all of this in order to find that information when you're doing examples, which we're going to do right now. Okay, so let's go. It says consider the vector negative 3, 2. Find the direction angle of that vector. Okay, so I'm going to do quick draws here. So if we do negative 3, 2, assuming that this is, the typical, so negative 3, this is 2 right here. So this would create the vector that looks like this, right? Okay, so that's our vector W. We need to find its direction, which is this. Okay, that's going to be the direction angle for this vector. But the formula that we use, theta equals the tangent inverse of the absolute value of b over a, is going to give us the reference angle for this vector. Well, what's the reference angle? It's right here. Okay, so what do? We plug in the values. This is a and this is b. So the tangent inverse of the absolute value of 2 over negative 3 is going to give us 33.7 degrees. So we know that theta in this problem is 33.7 degrees, right here. So if you recall, this is in quadrant 2, right? So if we look in quadrant 2, it says in quadrant 2, the direction angle is found by 180 minus theta. Now, could you memorize that? Absolutely. Do you need to memorize that? I don't think so. You could just simply draw it and know that when you look at this orange angle right here, the only way to find it is to do 180 minus 33.7, and you're done. So the direction is going to be 180 minus 33.7, which is going to be 146.3 degrees. So we have our direction for our vector. And one thing to take note of, because it's between 90 and 180, we know the vector has to be in, or the angle 146.3 is between 90 and 180. We know that it has to be in quadrant 2, which is why it's a valuable angle measure is very valuable for you, because it tells you where the vector is going to be by what it is. All right, let's try some more examples. Look at number 9 right now. So let's say we have a vector 5, -4. So let's put that somewhere. So we got about 5, we got about -4 here. So looks like we're going to end up over in quadrant 4. All right. So if we were to determine what the direction's going to be, it's going to be this gigantic angle. So we know the answer is going to be somewhere between 270 and 360. But if we want to find the reference angle, that's going to be this little angle over here. So how do we do that? Again, we're going to do, remember this is A and B, so we're going to do the tangent inverse of B over A, the absolute value of B over A, which is going to give us approximately 38.7 degrees. So this angle here, 38.7 degrees. So how do we find the direction? I'll put it in direction. Well, again, we could go back to the notes, and we could go, oh, I'm memorizing formulas. So the direction's going to be in quadrant 4, 360 minus theta, so we can just go ahead and do that. Or, without memorizing that, you can just look at the picture and go, well, how do I get that angle? I have to do 360 minus 38.7, which is going to give us 321.3 degrees as the direction of our vector, which is clearly between 270 and 360. So it's a good verification that happens. Let's do one more. So -1, -3, which is our AB. That's going to be -1 over here, -3 down here, which is going to give us this tiny little vector here. That. So we know that our direction is going to be this guy, which is going to be somewhere between 180 and 270. But we know that our reference angle is right there. So what does that look like? We got theta is equal to the tangent inverse of the absolute value of -3 over -1. This provides us our reference angle, which will be 71.6 degrees. This is not the answer, though. We need to find the direction, which is again, the orange rotation here. That's going to be... So we go back into our notes, we're in quadrant 3, 180 plus whatever that angle is. Makes sense, because if the angle's down here, we need to add 180 to it. So we're going to get 180 plus 71.6 degrees, which is going to give us 251.6 degrees as our direction angle, which is indeed between 180 and 270. Okay, this is indeed the longest lesson in human history, but obviously you have time to pause and everything, the videos as you go, so it shouldn't be so bad. You can break it up. So we have a couple more things to do that are similar to each other. First things, in the problems that we did before so far, I have shown you how to take a vector given its components, ai plus b times j, find its magnitude, and find its direction. You have all of the ability to do that. But what if they asked you to reverse the process? What if they gave you the magnitude and direction and asked you to find the original vector? Okay, that is the focus of this page in front of us. How do we do that? So first things first, there's a little bit of an edit here. So it says if we return to, just get rid of this here. And it should say if we return to page 23. Okay, I just forgot to edit this when I was redoing notes here. So if you return to page 23, so if we go, we're not going to go back, but basically it's for your notes. We talked about how to find the magnitude, okay? So if we wanted to know the length, so let's say we had this vector right here, over on the right over here. So this vector, right? We know that it was created as a resultant vector from the vectors A and B. So we know that their lengths are A and B. But if we wanted to know the magnitude of that vector, we would do the square root of A squared plus B squared, which is essentially just this symbol, the magnitude of V. So basically what we have right now is a triangle, a right triangle, that has 3 side lengths, A, B, magnitude V. So why are we using magnitude v? Because we could do square root of a squared plus b squared. We're just making it simpler for terminology speak. So what I'm going to do is I'm going to derive the formula for writing a vector in terms of its magnitude and direction. So how do we do that? We're going to use trig. So look at the reference angle we have right here in the actual triangle. Let's find the cosine of that. The cosine is always going to be adjacent a over hypotenuse magnitude of v. Okay, if we solve for v, or solve for a, we would just multiply both sides by the magnitude of v and get this for a. Let's do the same thing for sine. So the sine of theta is going to be opposite b over hypotenuse magnitude of v. If we want to solve for b, we're going to get magnitude of v times the sine of theta. Okay, so interesting development. If this is a and this is b, we actually have the components for the actual formula. So look, if this is ai plus bj, so ai plus b times j, we can just put in v cosine theta, which is here for a, which we did, and we can put v cosine magnitude of v sine b, which is here, theta, for b, and we basically have the formula. So all we need to do is this formula using the magnitude, so here's the magnitude here, and the direction is going to be theta, and we plug it into the formula and we get what the vector is. So what does that look like? It is a weird formula, albeit, but it's actually very simple. So it says write the vector v in terms of I and j, whose magnitude is 10 and direction angle is 120. Okay, so if this is v, that means the magnitude of v is equal to 10. And we know that the direction, which, this is a little confusing, which is we're going to use theta for the direction, is equal to 120. Now, let's pause button for a second on this. So note, in this formula right here that we use for the reference angle, we use the angle theta. Well, in this formula here, theta is the actual direction angle. So just make sure you don't confuse that when you're doing the problems. It's an easy thing to remember, but I could see somebody putting the reference angle in here. Don't do that. So what does that look like? So I'm going to write out the formula again since it's all marked up. So the formula is, for the vector, magnitude of v times the cosine of the direction angle times I, plus the magnitude of v times the sine of the direction angle times j. So we have that. We have 10 for the vector magnitude. We have cosine of 120 times I. Then we have 10 times the sine of 120 theta times j. No theta here, by the way. Oof, Jesus. Sine of 120 times j. All right. So just a note with this. Some of you are probably going to try to use the calculator to do this, and that's not a huge deal. It's just that some of these answers might come up as exact answers. Why? Because 120 degrees, remember if we want to convert 120 to radians, we would do 120 times pi over 180, right? And then if we do that, we're going to end up with reducing this is going to be 2 pi over 3. Okay, so technically, each one of these is actually 2 pi over 3, which means you can find exact answers for these. And if you did that, you would get 10 cosine of 2 pi over 3 is negative 1/2 times I. And the sine of 2 pi over 3 is root 3 over 2 times j. So remember, pi over 3... coordinate 1/2 root 3 over 2. 2 pi over 3 is in the second quadrant. So all student, you know the whole deal, right? Calculus. So sine is positive, hence it's positive. Cosine is negative, and we're taking the x for cosine and the y for sine. So if we do that, we're going to get negative 5i plus 5 root 3j. So what was I getting at here? So If you're using exact values, you're going to get a very nice exact answer, but if you decide to go in the decimal calculator route, you might get you're going to get a decimal answer for 5 root 3, but in a multiple choice question or My Math Lab, you might see this. So just be careful with that, don't get confused. They're just finding exact answers. So therefore, this is the vector that would have a magnitude of 10 and a direction of 120. Okay, so last concept in this section. It says one of the most important applications of vectors is the concept of force. A vector that represents a pull or a push of some type is called logically, force vector. Okay, so just a note. So let's say that you are let's say you have this lady over here who's holding a 10-pound package. That is the worst looking label of pounds I've ever seen. Okay, 10-pound package. Okay, so the idea from a gravity point of view is essentially there are two forces that are being acted on in terms of this package. You have a force of gravity that's equal to 10 pounds being pulled down, and then you have a force of your strength equal to 10 pounds that is pushing the package up so it doesn't fall. So most people obviously do not think of these things. They just pick something up and it is what it is. But in reality, that's actually what's happening is you need to exert the same amount of force on that package to even out the gravity's force that's pulling it down. And it's a big part of understanding that. It says if the package is not moving, it is assumed that the sum of the two vector forces, called the resultant force, is 0. So if this package right here is just stand still, that means that the resultant force of these two is essentially going to be 0. We also sometimes call that the resultant factor. So what we're going to do basically is that's just terminology, but we're going to run through a problem that deals with forces, and we're going to use that in order to review a lot of the concepts that we actually have done. So just realize that this problem is actually a pretty good one. I think you're going to see one much like it on your lab, but it sort of brings a lot of the topics from this section in and then applies it to this whole force vector stuff. So looking at number 12, it says two forces with magnitudes of 300 and 800 newtons act on an object at angles of 60 and 45 degrees, respectively. Okay, so that's the setup. So both of these are vectors because they have a magnitude in newtons and they have an angle in degrees. So that's the first thing, is understanding that these are clearly force vectors. But what's interesting about it is, what did they give you? They gave you the magnitude and they gave you the direction. So logically, look at A. It says determine the formulas for each force vector utilizing the formula as you see here. Well, what's this formula mimicking? It's mimicking this formula right here. So we're using this formula, so given its magnitude and direction, find the vector. Well, in this case, we have two vectors. One is basically the two forces that are acting on the object. So we have to figure out what that is. So for the purposes of this, I'm going to say F1 and F2 are going to be the two vector forces, or force vectors. So what's the first one? The first one is 300 newtons at an angle of 60 degrees. Okay, so we'll stick with that for now. We'll stick it in blue. So what does that look like? Well, the first thing is you take the magnitude, which is 300, you multiply by the cosine of the direction, 60 degrees, times I, and then you add the same magnitude times the sine of the same angle, 60 degree times J. Okay, so let's actually do the other formula first. So in green, we have the 800 Newton one at 45 degrees. So F2 is going to be 800 cosine of 45 degrees times I plus 800 times the sine of 45 degrees times J. Okay, so now it's just trig. So remember, 60 is pi over 3, and 45 is pi over 4. Luckily, we were in quadrant 1, so all answers are going to be negative. Remember, pi over 3 is 1/2 root 3 over 2. Pi over 4 is root 2 over 2, root 2 over 2. So the cosine of 60 is going to be the x-coordinate, which is going to be just a half. So we know that this is a half. We know the sine is going to be the other coordinate, root 3 over 2. Positive because of quadrant 1. We know both of these. Oop. Hold on, want to go green. Root 2 over 2, root 2 over 2. Alright, so just all you have to do basically is do the math for this. So we're going to get 150i plus 150 root 3j for our first value. And for, in green, our second value, we're going to get the same value for both, 400 root 2, for both components. Okay. A little bit of a weird eye. There you go. Okay, so that's a 2. So these are basically the formulas for our two vectors that are acting on our object. We won't need any of the information given anymore. We're going to stick to just having these two formulas for our vectors that are going to be used from here on out. Okay, so next it says find the resultant force. So what does resultant force mean? That is another term for addition of vectors. Okay, how do we know that? Because resultant vector was the addition of vectors. So we're going to let regular f be that vector, our resultant force. If you want to write f sub r or something like that, that's fine. But that's going to be equal to f1 plus f2. All right, so how do we add vectors? Okay, apparently we have a tornado warning today as I'm doing this because I just got that on my phone. You probably heard that. Anyway, f1 plus f2, we have our vector components. So remember, we're doing a1 plus a2, and then b1 plus b2. So what does that look like? It's going to be 150, which is our a1 here, plus our a2, which is here, 400 root 2, times I, plus we have our 150 root 3 for our b1, and then our 400 root 2 for our b2, times j. Okay, I don't even think we need the parentheses on this guy right here, right? No. Okay, so we got that. Now, hypothetically, this would be it, because we can't actually combine anything in here, but in order to do the calculations that are going on in the next two problems, we need decimals. So I know this is confusing because you're always trained not to do decimals, but what we're going to do for the sake of this is we're going to create an approximate vector. So if we put this right here in the calculator, we're going to get, I believe it's 715.69i. And if we put this in the calculator, we're going to get 825.49j. So this is going to be our resultant force for our problem. Next, we need to find the magnitude of the resultant force, which is our F. So we need to do the magnitude of F, okay? So not to be confused with magnitude of F up here. I know that's kind of, probably should use a different, let's do R, like I was saying, just to make sure. So resultant force is that. So how do we do that? Remember, that's the square root of a squared plus b squared. In this problem, we have a and b right here, so we're going to do the square root of 715.69 squared plus 825 plus 49 squared, which is going to give us approximately 1092.54, and that will be our resultant force for our problem. This is in newtons. Okay, and lastly, the direction. Okay, so this is where you just have to be careful. So what we need to do for this problem is do our typical direction formula, but that's going to give us the reference angle, right? So this is our direction formula. So what is our A and B? Well, again, they're right here and here. for our problem. Let me get it in blue so it's not too confusing. So A and B for our problem. So we're going to do the tangent inverse of the absolute value of 825.49 over 715.69, both positive, which is going to give us approximately 49.08 degrees. Okay, so this is our reference angle. So we don't know the direction yet. Technically we do, but depends if you're paying attention. So it turns out that if we're going to find the direction of the resultant force, then we have to look at what quadrant the resultant force is in. Since both the numbers are positive, that means it is in somewhere in quadrant 1, which means if you go all the way back to our problems that we were doing, these guys, what was the direction angle in quadrant 1? It was just theta. Right? So it's this scenario, which means in this problem, we know that theta is actually our answer. So the direction angle is equal to 49.08 degrees. So just note on here, this problem can be pretty confusing. The one in the lab I don't think it is in quadrant 1, so beware of that. So just to be clear, so it doesn't matter what quadrants the initial force vectors are in. It only matters if we're trying to find the direction of the resultant force, then we need to know what the resultant force quadrant is. We don't care about the original ones. So remember to look for that because you will have to alter this accordingly. It just so happens that it's exactly the same, but in a lot of cases it is not. So be aware of that, and I think on the lab it's not. So good luck.